everybody. I have a great pleasure and honor to be the chair of the 7th topic session. It's about theory and algorithms. I'm Marek Klonowski from Wrocław University of Science and Technology. Today we have scheduled 5 talks. 2 talks are before the break, then we have a short break, and then we have 3 remaining talks. What I would like to say, and I would like to remind you that we have opportunity to ask questions via Slack channel. There is a dedicated Slack channel called T07 Theory on the Slack, and you can just send questions and I will ask on behalf of you. So that's it for the introduction. The very first talk is entitled "On the Power of Randomization in Dynamic Networks with Adaptive Adversary." It is authored, the joint paper for Irvan, Jahja, Haifeng and Ruomu. There are guys from National University of Singapore. Irvan is going to present on behalf of authors. So please start.
Hello, everyone. My name is Irvan. I'm the presenter for today's talk. Here, I'm going to present our work titled "On the Power of Randomization in Dynamic Networks with Adaptive Adversaries." This is a joint work with Haifeng and Ruomu, and we are all from the National University of Singapore. We study distributed algorithms in the dynamic networks model, which is a flourishing topic in recent years. So this model is used to model networks whose topology can change over time. In the dynamic networks model, while the set of nodes are fixed and never change, the set of edges can arbitrarily or adversarially change from time to time. On a very high level, this work studies the power of randomization in distributed algorithms in dynamic networks with adaptive adversaries. That is, given some distributed computing problem, how much is the difference between the optimal mathematical algorithm for solving that problem if you compare it to the optimal randomized algorithm for solving the problem? We use the following standard dynamic rules. We consider dynamic network with n nodes, whose nodes proceed in synchronous rounds. In the topology can change from round to round, and we say that such a change is determined by some adversary. That is, the adversary chooses an arbitrary, connected, and undirected graph as the topology of each round. This is the only promise with the adversary. That is, the adversary promises that the topologies will always be connected and undirected. But aside from that, the adversary are free to change the edges from round to round. For the communication model, we use the broadcast congest model. By broadcast, I mean that in each round, every node chooses to either broadcast or send the same message to all its neighbors, or to receive messages that are being broadcasted by all its neighbors in that round. By congest, I mean the size of the message that a node can send is restricted to O log n. We study general distributed computing problems. By this general distributed computing problem, we mean problems where the output is some arbitrary function of its input. This covers problems such as sum, maximum, median, but it also covers many problems that are not typically defined as a function, like token dissemination. For these problems, we study their term complexity, that is, the number of rounds until all the nodes are. Our goal is to study the power of randomization in distributed algorithms in dynamic networks for solving these distributed computing problems. As a starting point, let's take a look at what happens in centralized algorithm. So in centralized algorithm, the deterministic algorithm has some associated worst-case input. That is, the input under which this deterministic algorithm performs the worst. So if you, in the centralized algorithm settings, randomness may help to deal with all these bad inputs, so to speak. But in dynamic networks, the situation is more complicated. You see, in dynamic network, if you consider a deterministic algorithm, there it has, in its worst case scenario, it has two components. First, it has the bad input, and second, it has also a bad adversary. Hence, it's not really clear how randomness can help to deal with both of them. So to illustrate this, let's take a look at a dynamic network example with 5 nodes that are trying to solve sum. Because it's trying to solve sum, each of the nodes have a certain input to the sum problem. As is read on this table on the left, this would correspond to the bad input part earlier. But in addition to having this input, there are also topology changes as chosen by the adaptive adversary. This is the bad adaptive adversary. And an algorithm for solving sum in distributed algorithm in dynamic networks can use randomness to potentially deal with bad input and potentially deal with bad adaptive adversary. Let's take a look at first how randomness can potentially deal with bad input. So for dealing with bad input, it's actually somewhat easy to see that the answer is yes, randomness actually does help deal with bad input. To see this, let's consider the equality problem defined as following. In the equality problem, in a network with n nodes, 2 of these n nodes are special nodes, and they each hold an input string of size n. These 2 special nodes want to know whether they are both holding the same input or something different. Using randomness and hashing, one can easily obtain an algorithm that solves this problem with high probability in just polylogarithmic number of rounds when the diameter is small. But on the other hand, one can easily prove an omega poly n lower bound for the time complexity of solving equality problem by deterministic algorithms, even when the diameter of the network is a constant. This then translates to an exponential gap in the time complexities between randomized algorithm and deterministic algorithm for solving the equality problem. This confirms our suspicion that yes, randomness actually does help to deal with bad input. But what about the bad adaptive adversary part? Can randomization help deal with bad topology changes as determined by the adaptive adversary? So an adaptive adversary can decide the topology of each round after seeing all the coin flip outcomes in all the past rounds and also in the current rounds. This suggests that randomness may actually help only limited power to deal with bad adaptive adversaries. This then prompts us to study. Is this actually true? Does randomness actually only offer limited help to deal with adaptive adversaries? Our contribution aims to answer this question. It turns out that, while on the surface the answer seems to be trivial, proving this is far from trivial, as we will see. First, we need to isolate somehow the randomness that is used to exclusively deal with adaptive adversaries from the randomness that is used to deal with bad input. The problem is that the algorithm can use the same randomness to deal both with bad input and with bad adaptive adversary, and so it's unclear how to isolate just the randomness that is used to deal with bad adaptive adversaries. To this end, we first define a simple notion of prophetic adversary. Prophetic adversaries, when deciding the topology in each round, can see all the coin flip outcomes, including the ones that are not actually flipped yet by the algorithm. Because of this, it's obvious that randomness is completely useless against prophetic adversaries. Now, with this notion in place, our idea is that to isolate the randomness used to deal with adaptive adversaries, given a consensus algorithm P for adaptive adversary, we will construct a consensus algorithm Q based on this P algorithm, but Q will work against prophetic adversary. We then will compare the performances of P and Q. Ultimately, our result is the following. We propose a novel design of algorithm Q based on algorithm P, such that the time complexity of algorithm Q is against prophetic adversary is only polylogarithmic and multiplicative factor higher than the time complexity of P against adaptive adversaries. This suggests that randomization can at most only improve the time complexity by a factor of polylog n. which confirms our suspicion earlier that randomization indeed only offers limited help to deal with adaptive adversaries. Next, I will give a brief overview on how we obtain this result. Though for this purpose, we will just use sum as an example problem. In a sense, given an algorithm P for solving sum in dynamic networks, with adaptive adversaries, we will design an algorithm Q based on P for solving the same problem in dynamic networks with prophetic adversaries. Our goal is to make Q's time complexity against prophetic adversaries as small as possible. Now, our goal is quite unique. We want to isolate the randomness that is used to deal with bad adaptive adversaries. Because of this, and also because the adversary determined its topology in an online fashion, it is unclear how to isolate this randomness using existing derandomization methods, such as conditional expectation, pairwise independence. Hence, we depart from such ideas and we use instead the idea of simulations in the following way. So, for designing Q, we initially have two things. One is the prophetic adversary against which Q is running, and the second is the black box algorithm P, whose guarantees are only against adaptive adversaries. First, we will specifically design an adaptive adversary phi. We will elaborate on this design later. Given this algorithm phi, Q will then simulate two things. First, it will simulate this algorithm. It will simulate this adaptive adversary phi, but it will also simulate P's execution against phi. So notice that there are actually two executions here. Q is running against prophetic adversary, but Q is simulating P, who is supposed to run against the adaptive adversary phi. Now, in order to simulate the execution of P over the adaptive adversary phi, Q will simulate this only by using simple floodings on the prophetic adversary. This is possible because we will design phi carefully so that Q can simulate P over phi with only simple floodings over prophetic adversaries. Now, simple floodings are just deterministic procedures, and so its guarantees must continue to hold even against prophetic adversaries. This is why a simulation will be good. The main challenge here is on how to design phi. The design of phi, among other things, will determine how efficient the simulation is going to be. There are many non-trivial challenges to solve in order to make this conversion efficient. All these challenges are explained further in the paper, but here we'll just, due to lack of time, we'll just give a small taste. Among other things, we want to ensure that phi has a small diameter, but in our design, we actually will eventually allow phi to occasionally have large diameter in some cases. In order to ensure that this won't cause problems, we will have some additional techniques to deal with it. Also, and somewhat interestingly, in our design of Q, we will actually sometimes simulate the execution of P against prophetic adversaries, even though P is designed only against adaptive adversaries. As a consequence of this, Q will end up using more coins than P, even though Q technically cannot use its coins to deal with the prophetic adversaries. All in all this technique combined and with very careful reasoning, everything will eventually go through. So to conclude, we have asked the following question for general distributed continuum problems, including maximum, sum, flooding. How much does randomization help deal with bad adaptive adversaries? We showed that the answer is that the help is only limited. That randomization can only improve the time complexity by at most a polylog n factor. This is the end of the presentation. Thanks for watching.
Thank you very much for your very interesting presentation. Now I would like to ask your questions. My question is about some specific problems. Namely, you have presented some generic methods to deal with the prophetic adversary, and doing this costs some randomness and so on and so on. Do you have some maybe idea, or maybe you know that for some reasonable classes of algorithms, we can do better, for example, with smaller amount of randomness to deal with this prophetic adversary? So my question is, can we do better for specific problems using similar methods?
Thanks for the question. So my understanding of your question is that our algorithm still use randomness against prophetic adversaries in the reduction, and you want to know if this existing randomness can still be further reduced. Is that correct?
Yes, if it can be reduced, for example, if we consider some specific problem, not a general problems, but some specific problem.
I understand. So the answer, the short answer is yes, we can do this for a specific class of problem. So the long answer is that well, we showed here that there are two things that randomization is used for in distributed algorithms in dynamic networks, against the input and against the adversary. Now we know that randomness actually helps against the input. So if you want to get a good performance against all input, you still need to use randomness. But for the class of algorithms, that somehow does not use randomness to deal with the input, I actually show in the standard version of this thing that sorry, I don't think it's in the standard version. I think it's in my thesis that for those class of problems you can actually turn the algorithm into deterministic one.
Oh, even that fully deterministic, yes?
Yes, but it's only for the class of algorithm that does not.
Oh yes, of course, yes. That's really interesting. And let me look if there are any questions. I think that the talk was clear and there was no questions up to now. But of course, you can contact the author directly. So, applause. Thank you for your very interesting talk. And now we switch to yet another talk. The second talk is LCP aware parallel string sorting, authored by Johannes Ellert, Jonas Ellert, Johannes Fischer, both from Technische Universität Dresden, Dortmund, sorry. And the third author is Nodari Sichinava from University of Hawaii at Manoa. So please, let's start.
Hello and welcome to this video presentation on LCP-aware parallel string sorting. My name is Jonas Ellert, and in the next 14 minutes I will show you the results of joint work with Johannes Fischer and Nodari Sichinava. Our paper focuses on the classic problem of lexicographical sorting, which I will explain with a simple example. Given a set of strings as input, we want to rearrange the strings such that they appear in lexicographical order, that is, in the same order in which they would appear in a dictionary. In our example, we have 6 strings over the English alphabet. On the right side, you can see these strings in the desired order. First the one starting with A, then the one starting with B, and so on. Note that the order depends on more than only the first character of each string. For example, string 4 and 5 share a prefix of length 4. In order to determine that string 5 is lexicographically smaller than string 4, we have to inspect the first symbol after the shared prefix, which is the letter A for string 5 and the letter B for string 4. Parallel string sorting is a well-researched topic both in theory and in practice. Since we are at the theoretical track of Europa, let's look at one of the best-known results in the PRAM model. If n is the total number of symbols in all strings, then the strings can be sorted in order of n log log n work and order of log n over log log n time. The time bound is optimal, assuming that the number of processors is polynomial in n. Hagerup introduced this result over 25 years ago, and even today there is no sorter that achieves a similar time bound with less work. However, we can improve the result by using a more realistic parameter to express the complexity bounds. Usually, the lexicographical order of the strings does not depend on all n symbols. In our example, the string S1 is the only one starting with the letter B. Therefore, in order to correctly determine the lexicographical rank of S1 among the other strings, we only have to inspect the first symbol of S1, while all following symbols are irrelevant for the ordering. In general, the rank of any string only depends on its shortest prefix that is not a prefix of any other string. If I highlight this so-called relevant prefix for all strings, then you can see that only 17 of the 34 symbols are relevant for the lexicographical ordering. We use the parameter d to denote the total number of symbols in all relevant prefixes. Ideally, the complexity bounds of efficient string sorters should be expressed as functions of d rather than functions of n. This is not uncommon in the sequential setting, where the strings can be sorted in order of d plus sigma time for an alphabet of size sigma. In contrast to that, we are not aware of any PRAM string sorters that exploit the distinguishing prefix. Our paper addresses this problem by introducing an algorithmic framework that creates D-aware PRAM string sorters from existing not D-aware solutions. The derived algorithms are work optimal with respect to their original counterpart. Given a string sorter that takes W of n work, the derived algorithm takes around W of d work. If the given sorter takes T of n time, then our derived one takes T of d times log d time, which is only by a small logarithmic factor slower than the optimal result. The rest of this presentation consists of two parts. In the first part, I will explain our framework on a high level, omitting technical details whenever possible. In the second part, I will show why the derived algorithms are work optimal with respect to their original counterparts. For the purpose of explaining the framework, I will keep using the example strings from the introduction. Initially, we have no information about the length of the relevant prefixes. As a first step, we use the given string sorter to sort the strings by their length 1 prefix. Now we can easily identify all strings whose length 1 prefix is unique. Consider, for example, the third string in the sorted list of strings. It begins with the symbol B. Since the previous string starts with an A and the following string starts with a C, we know that the third string is the only one that starts with a B. Thus, we have already placed the string at its correct position in the list of strings, and we do not need to consider it anymore during the rest of the algorithm execution. Note that in order to check if the considered prefix of a string is unique, we only have to compare the string with its two direct neighbors in the list, which means that given enough processors, we can check the uniqueness of all prefixes simultaneously. In our example, only the first character of string 3 is unique. Thus, the relevant prefix of any other string has at least length 2. Now we start increasing the length of the considered prefixes. Instead of only looking at the first character, we sort the remaining strings by their length 2 prefix. Again, this allows us to identify the strings whose length 2 prefix is unique. We compare each string with its neighbors in the list and find out that there is only one string starting with AA, only one string starting with AB, and only one string starting with CE. Both of the other strings start with CD, which tells us that the relevant prefix has at least length 3. However, in the next step of the algorithm, we do not sort the remaining strings by the length 3 prefixes. Instead, we double the length of the considered prefixes from 2 to 4. In our example, the two remaining length 4 prefixes are still not unique, so we have to double the prefix length one last time. Finally, all prefixes are unique, and the strings are lexicographically sorted. By using this doubling technique, we may inspect symbols that are not part of the distinguishing prefix. For example, the relevant prefix of string CDABAXXX is only 5 symbols long, but we still inspect all 8 symbols. However, it is easy to see that by doubling the prefix length in each round, we overestimate each relevant prefix by at most a factor of 2. Let us have a closer look at the total work that our framework requires to sort the strings. Before going into detail, I will introduce the necessary notation and recap the most important aspects of the framework. Our goal is to sort k strings named S1 through Sk. The relevant prefix of string Si is its shortest prefix that is not a prefix of any other string, and we denote the length of this prefix by Li. The size of the so-called distinguishing prefix is the sum of all Li. Our framework establishes the lexicographical order of the strings by repeatedly sorting them in a number of rounds, where we start with round 0. In round x, we sort the remaining strings by their length 2 to the x prefixes. A string that we considered in round x will be considered in round x plus 1 if and only if its length 2 to the x prefix is not unique. Equivalently, we could say that string si gets discarded in round log li. Finally, we write k subscripted with x to denote the number of strings that we have to consider in round x. The work required to detect duplicates in each round is negligible, as it will always be dominated by the more expensive cost of sorting. Therefore, we will only consider the work caused by using the given string sorter. To get a first idea of how we can calculate the total work, let us assume that this sorter takes order of n work to sort a string set containing n symbols. We sum up the work of all rounds, and in any round x, we sort kx prefixes of length 2 to the x. Thus, using our linear work sorter, round x takes kx times 2 to the x work. Now we will see that the sum is bounded by order of d. As a first step, we get more explicit about the work that each string contributes in each round. We still sum up the work of all rounds, but we replace the product kx times 2 to the x by instead explicitly adding 2 to the x work for each of the kx strings that we consider in round x. We can interpret these nested sums as follows. In each round, each participating string causes 2 to the x work. Alternatively, we could swap the order of the sums by interpreting the situation as follows. For each of the k strings, we have to add 2 to the x work for each round x that it participates in. Remember that string I gets discarded in round log li. Since now the inner sum adds up the first log li powers of 2, we can simply use the next larger power of 2 as an upper bound. Finally, 2 to the power of log li plus 1 is at most 4 times li. Now the sum matches the definition of d, and we have shown the desired order of d work bound. Of course, we do not actually have an order of n work string sorter, but the equation that we obtained here makes it very easy to determine the work bound when using real string sorters. I will place it in this red box here for later usage. Now let us see what happens when we equip our framework with Hagerup's string sorter that I mentioned earlier. It takes n log n work, which means that sorting in round x takes kx times 2 to the x times log kx times 2 to the x work. Remembering our red box, we know that for any x, kx times 2 to the x is bounded by 4d. This allows us to move the doubly logarithmic factor out of the sum. Now we are left with exactly the same sum that we have in the red box, which is bounded by 4d. Thus, the total work needed for sorting is order of d times log d. While we can use the same method to show the work bound for many other existing string sorters, we may have to slightly modify our framework if the work of the given string sorter not only depends on the number of symbols, but also on the number of strings. This is, for example, the case when using Jahja et al. String sorter. It requires k log k plus n work, where the k log k term is caused by the fact that comparison sorting is the underlying technique of the sorter. It is easy to see that for such sorters, the first rounds of our framework are rather wasteful. Take for example the very first round, in which we need order of k log k work to sort the strings by their length 1 prefixes. We could have just directly sorted the strings by their length log k prefixes instead, which asymptotically would have cost the same amount of work. Therefore, we modify our framework as follows. Initially, we sort the strings by their length 2 to the log k minus 1 prefixes, which takes order of k log k work. Then we continue with round log k of our framework, leaving the rest of the execution unchanged. This way, we skip the first log k rounds, and the required work for the remaining rounds is bounded by the sum that you can see on the slide. It already looks rather similar to the sum in the red box. Now we will see that in any round, the log kx term is at most 2 to the x. Trivially, log kx is at most log k. Since x0 equals log k, we know that log k is at most 2 to the x0. Finally, x0 is the first round that we perform. That is, in any round, x is at least x0, and thus 2 to the x0 is at most 2 to the x. If we take the sum and replace log kx with 2 to the x, then it is easy to see that the sum is at most twice as large as the one in the red box. Therefore, it is bounded by order of d. Together with the initial sorting, the total work becomes order of k log k plus d, which is exactly the desired result. I hope I could give you an understanding of how our framework yields work-efficient D-aware versions of existing string sorters. In our paper, you can find the full details, including the duplicate detection. Additionally, we cover the following topics. In this presentation, I omitted the fact that Hagerup's algorithm requires polynomial alphabets. This is a challenge for our framework and requires some additional processing steps. Another challenge are randomized algorithms, like the probabilistic version of Jahja et al.'s algorithm. Finally, we can also use semi-sorting and Raven fingerprints to compute a true approximation of the relevant prefix length. If you are watching this video at the Europa conference event, then you are invited to ask questions now. If you are watching this video after the conference event, then you are welcome to send me comments and questions via email. Thanks for your attention.
Thank you very much for your very nice talk. There are no questions for your talk. However, there is one comment from our General Chair Krzysztof Rządca. Namely, Krzysztof says there are no questions, but there are comments for you. That the presentation was exceptionally clear, and Krzysztof especially would like to thank you. This is also my impression. I have a feeling that I understood even details of everything. So thank you very much. No more questions. So it's applause for you. Thank you very much. And we would like to ask yet the last presentation. It's the talk about mobile RAM and shape formation by programmable particles. It is